So, um, so I've been looking forward to this since we started this semester, maybe since we started the year. Um, Proofs are my favorite part of pre-calculus because this is where I get to watch you guys blossom into like real mathematicians. We are going to do some actual math. This is not me give you a formula and you plug numbers into a formula and punch buttons on a calculator and give me an answer. This is like real deal mathematical struggle and reward at the same time. Um, you are going to use every algebra trick that you know in this unit and also a whole bunch of trig stuff that you're going to be learning as you go along. Um, so I got to start with a little pep talk because I will tell you this is going to be different from what you're used to in your math classes. You guys probably up to this point, the majority of the stuff that you've learned, um, your teacher has explained it to you, and either on that day or after you've had a chance to practice and ask some questions, at some point it clicks into place, right? You can feel that light bulb turn on in your head, and you're like, oh, I got this. Proofs are not that way. They are going to slowly grind into place, and eventually you are going to become proficient and comfortable with these things, but it's a process. It's not going to happen today. It's probably not going to happen this week. And that's okay, because that's just the nature of what actual mathematicians do. Um, so please don't beat yourself up if you walk out of here today and you're like, I don't feel confident at all that I'm going to be able to complete this assignment. And if there's 10 proofs on your assignment for today, if you're able to complete and feel confident about half of them, you should consider that a win. I want you to try every single one and see how you do, and come in with some questions. But if you can complete half of them, then you should be feeling pretty good about yourself. And if it's less than that, that's okay. But you're just going to have to trust that this is going to kind of grind into place. It's going to be difficult. For most people, their growth is kind of slow and steady with this, and that's tough because you don't get to kind of see that like immediate reward for your efforts. But I promise me that a couple weeks from now, when you look back, you will recognize that you are better at this 2 weeks from now than you are today. Okay, so I want you guys to remember where you're at today. Take a mental picture in your mind. You've never seen a trigonometric proof before. I am going to be asking you guys for some advice for my future students in a couple weeks. So remember this moment so that when you're pros in a couple weeks, you can give me some sound advice from a student's point of view about how they can get through it. So there's this thing. Have you ever heard of QED before? It's Latin. And a lot of times in math, at the end of a proof, they will put QED. It stands for Quod Erat Demonstratum, which translates to that which was to be demonstrated. And it's basically like the mathematical mic drop. You're like, there it is. You're welcome. And so like, when we finish these proofs, we're going to be putting QED at the end of them, and we're going to feel really good about it because it ain't easy. So let me give you some advice. Invest in a good eraser. Please do not use pen for this. You're going to be erasing a lot. Proofs are messy. If you're the type of person that likes to keep nice, clean, pristine notes, I suggest have some scratch paper on hand, or maybe just grab a cheap spiral notebook from the dollar store and use that as your proof notebook. Keep it in a separate spot. Okay, but these things are not neat. I have a lot of students that really love to conserve space in their notes. I encourage you, don't worry about that. Worry about understanding and trying things. Leave yourself some space. This is important. You are going to struggle through this, but as you struggle, you are learning. So it is productive struggle. They say this a lot in the tech world or the business world. Fail early and fail often. You're going to learn from your mistakes. Get out there and make them as quick as you can. Okay. Every time you go down a blind alley, you're gonna learn something from that that's going to help you later on. You got to be patient with yourself and trust that you are going to understand this. Every proof that you finish, celebrate it. Give yourself a pat on the back. It feels good to finally get one of these things to work. I don't want to scare you. There's going to be some of these that are going to take 2 or 3 steps, and you're going to be like, that was no big deal. Okay? But not all of them. Trust me. Use your resources. So you've got examples that we're going to be going over in the notes. I've chosen these examples because they utilize a lot of the strategies that you're going to be using in your assignments. There are also examples in your textbook, and I don't tend to use the same example in our notes as they do in the textbook because I want you to have an opportunity to see both of those. So don't forget that there are a whole bunch of proofs in section 5.2 in the textbook that you can go and look at if you get stuck. The identity sheet, like I said, you need to start familiarizing yourself with this. Focus on the top half for now. The quicker you can get familiar with these things, the quicker you're going to be. When you see me working through a proof and I'm able to do it really quickly, it's because I basically have this stuff memorized. And I've used every one of these identities so many times that I know like when it's useful and when it's not. You will get there, but that's going to take some time. But the more you can do to try, for example, if you run into something and you see some squared stuff, I'm hoping at this point when you see squared stuff, you're thinking Pythagorean identity. Before you go to your sheet and start looking up the Pythagorean identity, see if you can remember at least what the first one is. Like mentally try and recite that sine squared plus cosine squared equals 1 before you look at your sheet. That's going to help you to start to memorize these things and again become more familiar with them. This is important. You can't learn this by copying someone else's work, so I'm not going to be posting solutions to these things online because it does you no good to just look at my answers. Okay, when we come in each day, and the other thing is that I'm not going to go through and do proofs at the beginning of class. So when I ask for questions at the beginning of class, I will not be completing an entire proof. What I will do is I'll give you some hints. And I'm going to try my best to model the type of hints that I want you to be giving each other too. Okay. A productive hint is something like you're going to end up using a Pythagorean identity in this thing. Or it's going to be important to factor out a GCF at some point. Or you'll end up multiplying by a fancy 1 so you can combine 2 fractions into a single fraction. Those kind of things are productive hints. Telling somebody like the categories of identities that they're going to use is much better than saying, oh, just multiply by cosine minus 1 over cosine minus 1. Okay, so give people productive hints. That's what I'm going to do for you guys as well. If somebody asks you, help them out, but don't just give them the answer because that's not going to help them learn in the long run. And it's not impressive either. Spoilers are not impressive, so no spoilers. I'm going to ask you guys today as we're working through to think about what you might be using. I don't want people shouting out answers today. If you've got to get it out and you just can't hold it in your head anymore, jot it down on the side of in the margin of your paper. But the reason I'm asking that is because I want to give everybody a chance to kind of think through what's going on and what we should do next. All right, so that's the mindset stuff. There are some rules that I am going to enforce on this. This first one is a general rule with proofs. How these things are going to work, if you look down at the 4 examples, you're going to be given an equation. This is called an identity because this side is identically equal to this side. All right, and your job is to prove that these 2 things are equal to each other. Your job is to string together a bunch of small steps that take us from one side of the equation to the other side of the equation. Okay, so you know the nice thing about these that was not in your assignment that you worked on from Monday is you know where you're going. You know what the final result is going to be. The thing that's not so nice is it's not nearly as simple as a lot of the results were that we did from 5.1. So when we start these, you get to choose which side of the equation you want to work on. We do not work on both sides of the equation at the same time and try and meet up in the middle. That is not how we do proofs. Okay, now you can start on the left or you can start on the right, but once you've made your choice, if I choose to start with this, I only get to play with this side of the equation until I can make it equal to this. Okay, do you guys understand what I'm saying? A lot of times at first people want to start messing with both sides of the equation, and then once they get something that equals to each other, they think they're done. Now, it is a viable strategy, but in your final answer, I need you to make it look as if you're only playing with one side of the equation. So there is a strategy that's on your proof sheet that says try working the other side of the equation and see if you can get things to meet up in the middle. And we'll see an example of that today. But the rule is for our final product, we only get to work on one side or the other, and we are going to format it exactly as we did last time. So you'll write one side down, you'll manipulate it to the right of it, and then going down in a vertical column with your equal signs lined up until you arrive at the other side. Only one category per step. And this last part is, we've talked about this before, our goal here is clear communication. It's not about getting the right answer. The answer is here. You already have the answer. Okay, so this is more like, your final product is more like an essay in English than it is like solving an equation in math. Neatness counts and format counts. If you're working and you're like, should I show this as one step or two steps? The safe answer is two. Okay, we're not trying to rush through these. We want to make a nice, slow, steady explanation of why these two trig expressions are equal to each other. So that's it. That's the rules. That's my pep talk. You guys are going to do awesome at this. You're going to enjoy it. Think of these things like those super fun brain teasers that everybody loves doing, and just enjoy the process. So we're going to get started. Does anybody have any questions? Are you guys feeling good about this? Are you excited? Today you become mathematical explorers. All right, let's do this. This is our 5.2 notes. We are going to do these on a separate sheet. The reason is it's unpredictable how long these things are going to take, how much space they're going to take up. You might notice that I have switched over to a pencil. This is probably the first time this year that you've seen me write in pencil instead of pen. There's a reason for that. Pen shows up better on the camera and on the screen, but we're going to make some mistakes today, so I want to be able to erase it. So let's write down. This is what I would like to see on your assignments too. You're going to write down the original equation, and then underneath that you are going to start your work. All right. So we want to choose a side to start on, and I'll give you some advice about how to choose which side you start on. Typically, you want to start with the most complicated side because it's easier to take something complicated and make it more simple than the other way around. So typically, you want to start on the more complicated side. When I'm talking about complications, what I'm talking about would be terms. Terms are things separated by a plus or a minus. When I look at this one, I think this side looks more complicated because it has two terms. This one only has one term. If I see anything with a fraction, I'm usually going to start on that side. So in example 3, I'm going to probably start on this side. In example 2, I'm probably going to start on the right side. If I have multiple fractions to choose from, the more complicated fraction is usually the one that has more terms in the denominator, right? Because this is simple, you could split that up into two fractions and make that look a lot nicer. So on example 2, I'll probably start on that side. So typically you want to start with the more complicated side, but all of these proofs can be worked both directions too. So I'm going to choose to start here with tangent x plus cotangent x. So let's write it down. Now I do want to see the original identity written before you start your work. That's important because when you come back to look these over later on, it makes it easier to see what we were going for. As we complete this proof, all of our work is going to be in the right-hand column. I know it's going to bother you, some of you, that you have all this blank space here that we're not utilizing. I know, but it's okay. It's okay. All right. So here we go, guys. I would like you to think about, without shouting out, what category of identities, and you guys, I see you all have your pink sheets out, most of you do. If you don't, I would make sure that's visible to you. What category of identities could be potentially useful to us here? Any ideas? Quotient? Yep. Yep. Let's try and not shout stuff out. I know it's tough. It's tough because you're like, quotients. All right, quotients. Yes, let's do quotient. What are you guys thinking quotient? Yeah, let's turn it all into sines and cosines. Tangent sine over cosine. Cotangent is cosine over sine. All right. I'm thinking about where to go next from here. Don't forget, on the flip side, there's some proof strategies. So if you ever get stuck, I would be looking at this list here. And the first one on the list is add fractions, get a common denominator. And I think that applies to this situation. One thing that I need you to keep in mind always is where we're headed. When I look at my final product, the thing that my target expression here, I notice that it's all one term. There's no plus or minus in this. So that leads me to think that somehow I need to combine these two things together. And we could do that potentially by getting a common denominator and creating a single fraction. That's going to move us in the right direction. So let's do that. So I'm going to rewrite, when we get a common denominator, I want to see explicitly what's your fancy one that you're multiplying by. So here's my original. My original two terms, and we're going to strategically multiply each of these by a fancy version of 1 so that we can get a common denominator. And I'm going to go ahead and write down my next step with my common denominator. What is the common denominator we're shooting for here? It's going to need a cosine, right? And it's going to need a sine. So cosine sine? Yeah. All right, so what do we need to multiply our first term by here so that we have both a cosine and a sine? It's already got the cosine. It needs a sine, doesn't it? So let's make this fancy one a sine x over sine x. And this one's got the sine. It needs the cosine, so we'll make this one a cosine x over cosine x. Just double checking, are we going to end up with two fractions that both have sine x and cosine x in them? We are. And let's figure out what our numerators are going to be, and we can just bring it together into one single big happy fraction. This is sine squared x, and this is cosine squared x. Bless you. Ooh. I always get excited when I see sine squared and cosine squared together. What does that make you think of, sine squared and cosine squared? Don't shout it out. Point it out on your paper. Are you thinking about Pythagorean? Yeah, sine squared plus cosine squared is equal to 1. Isn't that beautiful? So that turns into a 1 on the top. And keep in mind what we're going for. We're trying to make this thing look like secant times cosecant. And can you kind of see how that's going to end up happening? So I think what I'm going to do next is split this into two fractions, 1 over cosine and 1 over sine. And then in our final step, we can change those into secant and cosecant. All right, QED. You're welcome. Doesn't that feel good? We did our first one, guys. Nice job. Um, any questions on that? Thoughts, comments, concerns? What do you think? Is this kind of cool? So a couple of things. If I wanted to give a productive hint for this thing, if you were working this on an assignment and you had completed it and your buddy was like, I am totally stuck, I'm not sure what to do, can you give me a hint? What would be a nice productive hint to give that wouldn't be a spoiler? Any ideas? What do you think? Yeah, I think that fancy one is going to be pretty key. You're going to end up using some fancy ones here. That'd be a great hint. Any other ideas for a hint? I think common denominator would probably be a pretty good hint here too. You're going to end up with some fractions at some point. You want to get a common denominator and combine them together. If you're unsure of a hint to give somebody, a decent hint is always just tell them the category of identities they're going to use. You're going to use quotient identities. You're going to use Pythagorean identity. And you're going to use some reciprocal identities. And that'll give them sort of a place to kind of focus their attention on that identity sheet and help them along. So, okay. All right, let's move on. How much space do I need for this? It's really hard to predict. I didn't tell you this, guys, but normally before the first time I teach a lesson, I go through and rework all the examples just to make sure that I got it down and I'm not going to make a bunch of mistakes. But I purposely did not today because I wanted this to be as authentic as I could make it. And I'm going to tell you that there's probably going to be a point at which I'm going to get totally stuck today. But that's all right. I've got 18 of the brightest minds at Ferndale High School here in the room with me, and you guys will help me through it. All right, let's do example 2 here. We got cosine x over 1 minus sine x. 1 plus sine x over cosine x. All right. I do not remember how this is going to go, but I'm confident we can get there. So our first order of business is to choose which side we want to start from. And I am looking at the left-hand side this time. It seems more complicated because it has 2 terms in the denominator. 2 terms in the numerator is usually easier to deal with 2 terms in the denominator. So I'm going to go ahead and start on this side. All right, and I am up for suggestions. Any ideas? Any ideas? Even if you're unsure, I'd love an idea. This is usually the one where we have the opportunity to try something out that doesn't work. And it's okay. It's going to happen a lot. So let's do our first one here. Someone give me an idea. What can we do? What can we do? Well, what options do we have on the table? All we're dealing with here is a cosine and a sine. So, I mean, I could turn cosine x into the cosine of negative x. That's a possibility. What else could I turn cosine x into? I could turn cosine x into the sine of pi over 2 minus x. Could do that. Does it seem like that's going to be helpful to get us where we're going? No, probably not. I could turn cosine x into 1 over secant x. If I made this into 1 over secant and I made this into 1 over sine, or sorry, 1 over cosecant, is that going to get us where we want to go? Maybe. We could try it. Not really seeing a whole lot of other options here. Let's flip the sheet over and see if there may be some guidance on the back here. I see something in this bullet list here that is going to definitely be helpful to us in this problem. Which bullet do you think might be helpful to us? We want to eventually get a monomial denominator. That's ultimately what we got to do. But there's another one that's gonna. There's one of these up here is going to be helpful for us to get there. Do you see it? It's actually the one that's right above it. It's that third bullet point. So I talked at the end of the lesson on Monday about how I need you guys need to just get super familiar with these shortcuts. When I look at this, I see 1 minus something. That's kind of like my a minus b. If I could take that and multiply it by a plus b, then I can turn that into a squared minus b squared. So if I multiply this by 1 plus sine x, I could turn it into 1 minus sine squared x. And then I think we'll be able to use a Pythagorean identity. So how did I know to do that? I've done a million of these. When I see 1 minus sine x or 1 minus cosine x, oftentimes you're going to end up multiplying by a fancy 1 so that you can use your difference of squares shortcuts. So let's go ahead. I'm just going to rewrite this because we're going to multiply by a fancy 1 here. We're going to multiply by 1 plus sine x over 1 plus sine x. And we are using, this might be helpful to put on the margin of your notes, we're using the fact that a minus b times a plus b is equal to a squared minus b squared. So let's look and see what that does for our denominator. So 1 minus sine times 1 plus sine. So you're just going to end up with this thing squared minus this thing squared. So that would be 1 squared, which is 1, minus sine squared. Any questions on that step? Compare where we're at to where we're trying to get to. I'm feeling pretty good about this. In my final step, I want to have a 1 plus sine x in my numerator, and we do already. That makes me feel pretty good. I feel like we're on the right track here. We need to somehow end up with a cosine x in the bottom. I'm hopeful that when you see 1 minus sine squared x, you're thinking about Pythagorean identities. If you manipulate the primary Pythagorean identity, what is 1 minus sine squared? 1 minus sine squared is cosine squared, yeah. 1 minus, if we were to subtract sine squared from both sides, this would be 1 minus sine squared, this would just be cosine squared. So 1 minus sine squared turns into cosine squared. Keep an eye on what we're trying to get to. I think we're almost there. We got our cosine on the bottom. We got too many of them, but one of them is going to cancel with this one up top, and then we'll be there. Hey, hey! Second proof done! So this one is a little bit trickier. How did I know to multiply by this fancy one? Again, it's just experience. I've seen this come up enough times that I know that if I have 1 minus sine or 1 minus cosine, that I can do that. It will also work with things like if I had secant minus 1 or secant plus 1, or if I had cosecant plus 1 or cosecant minus 1, you can multiply and get this kind of difference of squares things to work out for you and end up at one of those Pythagorean identities. If you were going to give a productive hint to somebody about this one, we might say something about multiply by a fancy one, and I would probably give as a hint, try and use the a minus b, a plus b shortcut to set up a Pythagorean identity. All right, there's number 2. You guys feeling okay? Do we need to take a break, or can we keep going? We got this? All right, let's keep going. You guys are doing awesome. We got 2 more, and then my hope is to give you a bunch of time to start on your assignment. Help each other out through that. So this is example number 3. We got cotangent squared over 1 plus cosecant. So we got to choose which side to start on, and I am thinking I'll start if there's a fraction. Usually I'll start with that. This is a fraction, and it has 2 terms in the denominator. I'd say this is more complicated. This looks a little bit longer, but this is more complex. So I think I'm going to start here. And we'll see what we can do. So as somebody who's done a bunch of these, and so I'm looking at this thing right now, and I'm like, ooh, maybe I should have tried these before class, because I don't know. I have no idea how this is going to shake out. As I'm looking at this, a couple things that I noticed, we do not want a fraction here. I do not want a fraction here, so I'm hoping at some point we're going to be able to cancel some stuff. We're going to make this is going to probably remain a fraction for a while, but I'm hoping at some point we'll be able to cancel some stuff. The only way that's going to happen, though, is if I can turn this binomial into a monomial. And that is, I believe, one of the hints on the back of your identity sheet is to create a monomial denominator. The reason typically that we want to try and create a monomial denominator is in the hopes that that single thing that we get down here will cancel with something up top, and then we don't have a fraction anymore. And we're going to have to get to something without a fraction eventually. So that might be where I focus my attention at the beginning, is on my denominator and trying to find a way to make this a monomial. The other option that I can see going forward here would be we could turn everything into sines and cosines. This could become sine or cosine squared over sine squared. This could become 1 over sine. Is that going to help us? I don't know. What do you guys want to do? those are our two options, is to try and work on this to make it a monomial, and I have some ideas for how we might accomplish that, or to turn everything into sines and cosines. And I have a feeling that would work out too. It's more of a hope than a feeling, but it's all right. What do you guys think? Nobody wants to weigh in? Toss a coin. Dun, 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 dun. That's all right. I'll wait. I'm patient. Someone's got to make a decision. For the greater good. What do you think? What would you... Ooh, you thinking of a 1 minus cosecant squared? I like it. Was anybody else thinking about that? That was kind of my idea for turning this into a monomial. We saw that happen in the last problem, right? In the last problem, we had a 1 minus sign and we multiplied it by a 1 plus sign, and that was able to, by that, we were able to turn this binomial into a monomial. I'm thinking we may be able to do something similar to that as well. I'm not 100% sure. I'm hoping that we get something that's one of our Pythagorean identities by doing that. But I love it, yeah. So you're already bringing in a strategy that you've seen work previously in another proof. And that's kind of the key. So let's give it a shot. I'm not 100% sure if this is going to be the way to go or not, but we've seen it work once, so why not try it again? So let's multiply it by its conjugate. So we're using that a plus b, a minus b thing again. So I've already got the 1 plus cosecant. Let's try multiplying by 1 minus cosecant. All right. Let's see what happens here. My new denominator is going to be, again, we're using this a minus b, a plus b is equal to a squared minus b squared. So my a is 1, a squared would be 1, minus b is cosecant, so cosecant squared x is my new denominator. We'll mess with that in a minute. Let's decide what to do with our numerator right now. In this step, all we're doing is like multiplying and simplifying. So I could go ahead and distribute that cotangent squared x right now, or I could leave it factored out. I'm kind of thinking about leaving it factored out because in my target expression, it has something that's factored, like a GCF in front of a binomial. So I'm kind of thinking about leaving this in that same format for right now anyways. So I think I'm going to go just leave it factored out. So cotangent squared x, 1 minus cosecant x. So our hope is that this 1 minus cosecant squared x is going to be one of those Pythagorean identities, and we can turn it into a single term. So look at your Pythagorean identities and see if you can find the one with cosecant squared. Can we manipulate this so that it's 1 minus cosecant squared? Yeah, what would it equal? If I manipulated this so that it was 1 minus cosecant squared, it'd say 1 minus cosecant squared x equals what? Cotangent? Close. Negative cotangent. If that doesn't make sense to you, you may need to actually show some work here. If I did minus cosecant squared x on both sides and minus cotangent squared x on both sides, the cotangents would cancel, the cosecants would cancel. I'd have a minus cotangent left here and a 1 minus cosecant left over here. Okay. I usually will not show these steps. By now, I'm hopeful that we are comfortable manipulating an equation like this, moving things from one side to the other and switching signs. All right, so are we in agreement that we can call this negative cotangent squared? Let's do it. So I've got cotangent squared x of 1 minus cosecant x over negative cotangent squared x? Oh boy. All right, now I'm getting a little nervous. Okay, yeah, this is good. This is good. Hey, we got it to a monomial. I'm sorry. I'm looking a few steps ahead, and I'm starting to feel a little bit nervous here. But if I think about where we're actually at, I think we're in good shape. We've got the format starting to resemble what this looks like over here, and this is a monomial, which means we can probably get it to cancel. In fact, I'm seeing it cancel with this cotangent squared. Are you guys seeing that too? That's going to cancel, and I'm going to be left with a negative 1 on the bottom. What worries me is I want a cotangent in my answer. So I kind of didn't want the cotangent to cancel, but it's gonna. So I think we just keep going. So those are going to cancel. I'm going to end up with a negative 1 on the bottom. It's okay. It's all right. I've got a negative 1 down there. It's going to be all right. We got this. And then, well, I guess when you divide by negative 1, you just flip signs, right? This is going to become a negative 1, and this is going to become a positive cosecant. Why don't we go ahead and make that change? I'm going to rewrite it as cosecant x minus 1. I'm basically distributing that negative 1 and rearranging the terms. So, okay, so now this is interesting because we made it a lot simpler, but now we need to somehow make it more complicated. We somehow need to get cosecant x minus 1 to equal this, okay? And I'm going to be honest with you, I got no idea how to make that happen. So, but this is a wonderful opportunity for me to show you our other strategy, one of our other strategies, which is I told you we have a hard and fast rule that we can only work on one side of the equation at a time, right? In our final product, I can only work from here, and I somehow have to make this equal to this. But what we're going to do is on a separate sheet of paper or in the margins, we are going to sneakily work on this side of the equation. If we can find a way to make this equal to cosecant minus 1, then we can just reverse those steps and put them down at the bottom of this page. Does that make sense? So this is going to come up sometimes where you're like, I think I'm on the right track, but I have no idea how to connect this back to here. So this is going to be my scratch work. My target now is to get a cosecant x minus 1. And I'm going to start with the other side of my equation. So the rules say we're only allowed to work on one side of the equation, but that just applies to our final product. Sometimes you got to start at the end and work your way backwards. So can I make this look like this, and then we'll just reverse our steps? So I think this could be possible. I think it's doable. So what am I going to do? Let's maybe, you guys want to do sines and cosines or distribute maybe first? Maybe distributing would be a good idea because right now it's got two factors. We want it to just be two terms. What do you think? Distribute? Let's try distributing. Cotangent x secant x minus cotangent x tangent x. Remember, we're trying to get to where we left off, this cosecant x minus 1. Turn everything into sines and cosines. All right, now technically we're going to have to do this in 2 steps because these are quotient and reciprocal identities. So we're going to go cosine, sine. We'll leave this as secant for right now. You know what? I'll tell you what. I'm going to bend the rules, and I give you permission to do it as well. I'm okay with you combining reciprocal and quotient identities in the same step. Secant 1 over cosine x. We're trying to get cosecant x minus 1. Are you seeing it? Are you seeing it? Is it clicking into place? See how these cosines are going to cancel and we're going to be left with 1 over sine x, which is cosecant, right? And cosines are going to cancel, sines are going to cancel there. That's just 1. All right, I think we're ready to finish our proof, right? So I'm going to keep this off to the side, and I'm going to basically take these 4 steps. Wait, 1, 2, 3, 4, and I'm just going to reverse the order. This is going to be the next one, and then boom, boom, and this will be our last. So from here, I'm going to turn this into 1 over sine x minus 1. Would have never thought to do that. And then what am I going to do here? Now, how would we actually accomplish this? I think I'm going to modify this way that this looks a little bit. I'm going to, instead of 1 over cosine over sine, 1 over cosine, I'm going to do 1 over sine and then cosine x over cosine x. It's all the same stuff, right? Is what I had here on my scratch work. This is all the same stuff. But I think it makes more sense to have your 1 over sine x and multiply by a fancy version of 1 here. And this 1, I'm going to write as, sorry, that should be a minus. Well, I'm going to just write it as we had it. Cosine x sine x over sine x, or times sine x over cosine x. I mean, that is 1. How somebody would ever come up with the idea to turn this into this, I don't know. But it works, right? It is true. So yeah, so again, this is, if anybody's a little confused why I didn't copy this down exactly as it was, I think it would be quite a leap for somebody to go from 1 over sine x and go straight to this. Right? It would be hard for me to see why I could go from 1 over sine x to this. So I'm actually going to do it in 2 steps. I'm going to think of it as 1 over sine x, and what I noticed here is that I do have a cosine x over cosine x here. So I'm going to think of it as 1 over sine x times a fancy 1, and then I'm going to rearrange this so that it looks like this in my next step. So in my next step, I'm going to rearrange this to cosine x over sine x, and then 1 over cosine x. And then I'm just going to copy my last 2 steps from my scratch work over here backwards. This is cotangent x. This is secant x. This is cotangent x, and this is tangent x. And then we can finish this up by factoring out a cotangent. Whew, it's a good thing I started this on a fresh sheet of paper. We took almost the whole thing. All right, that one got messy. Thank you guys for sticking with me on that. I chose this one in particular for our notes, because I knew it was going to be messy. Every year we've had to do what we just did. I've never been able to get this to work out nice and simply. I've always got stalled out at this point where I'm like, I don't know where to go from here to get it to where I'm trying to go. So this is a good one, good example of sometimes you gotta work the other side on a separate piece of paper and the margins, and then try and get the two sides to meet up in the middle and then reverse. When you reverse those, sometimes you have to do a little bit of modification, because remember, if I had left this step out, I would say it's a pretty big leap for me to go from 1 over sine x to cosine over sine times 1 over cosine. That's just too big of a step. I wouldn't understand how you're going from here to here. That's just so what could we do in the middle to kind of make it a little bit easier to digest? Well, if I multiply this by a fancy one that was cosine over cosine, then I would at least get all the stuff that was in this, and then this would just be rearranging. So that's why I chose to include one more step in there, because ultimately we got to keep in mind what's the goal here is to communicate. How do we get from one side to the other? All right, you guys are doing great. We got one more. Any questions on this one? You're not going to see anything quite this intense on your first assignment. Okay. Not on the first one. Have I talked to you guys about what this is going to look like on the test? I don't want you guys thinking about the test right now, because that just tends to stress people out, the idea of trying to pull one of these things off on a test. But just to put your mind at ease, when we do our test over this, there will be 3 proofs on it. But for each of them, there will be 2 options. They are on the shorter side, 5 steps or less. So that last one would not be on a viable test question. And for each of them, there's 2 options. And the reason for that is sometimes you get stuck. So you're going to have 2 different proofs that you get to choose from for each of the 3 proofs. Does that make sense? So you'll look at it and you'll be like, "Ooh, I think I know what to do on this one." And you'll start working it. But if you get stuck in the middle and you just can't figure out where to go, then you got another proof that you can try. You can do that one instead, and then you'll just circle the one that you want. Usually a lot of times people will do both proofs for each problem and circle the one they want me to grade. Circle one they're most confident in. It's very rare that I have somebody who can't get at least halfway through one of the 2 proofs. Very rare. Okay, so you guys are going to get there. But don't worry about the test for now. I got you covered. Trust me. I got you. Okay, example 4. This will be our last one together today. We're going to try and prove that 2 times the cotangent of any angle times the cosecant of any angle is equal to 1 over the secant of any angle minus 1 plus 1 over the secant of that angle plus 1. Interesting. Choose a side. I'm going with the right-hand side this time. Yeah. Now I'm still going to put it on the left. But I'm starting on this side this time because it's got fractions. It's got 2 different fractions. Those fractions have binomial denominators. There's all kinds of complication going on in this thing. All right, we're looking for some viable proof strategies here. If you get stuck on, please, when you're doing your proofs, don't get stuck on this side. Make sure that you're reading over the proof strategies as well. I see a couple things that might be useful to us here. Well, the first one looks like a very useful hint, right? Add fractions to get a common denominator. We have 2 fractions. We know that we're trying to get a result that's a single term, so maybe if we could combine these 2 fractions into a single fraction, that would move us in that direction. There's another thing on here that I'm seeing that's probably going to end up being helpful, I think. I think this a plus b a minus thing may come into play here as well, because when I look at these two denominators, we'd have a plus b and a minus b. So yeah, I'm thinking get a common denominator. That seems like a good step for our next step. So let me write down our original fractions. And I'll leave space for a fancy one after each of them. Oops, this one's plus. I think we're going to use that a plus b, a minus b thing here, right? Because if I multiply this one by secant x plus 1 and this one by secant x minus 1, then both of my denominators have both versions with the plus and with the minus. So they've got a common denominator. So it got kind of messy, but things are going to simplify a little bit, because what do we get when we multiply secant x minus 1 times secant x plus 1? Secant squared x minus 1. That's that a plus b, a minus b thing showing up again. Third time today. You'll see it a lot. What do we got left over on the top here? 1 times that would just be secant x plus 1. And this would be secant x minus 1. Ooh, look at that. We got some canceling that's going to happen. Minus 1 and plus 1. I like that. Ooh, and check this out. I got a secant x and another secant x. We're going to be able to combine those together and get 2 secant x, right? That's going to get us the 2 that we want. Remember, we always got to keep our eye on where we're headed. So I'm seeing where the 2 is going to come from. It's going to come from combining these two. Well, let's go ahead and combine like terms here. I'm getting excited. Starting to see the light at the end of the tunnel here. Secant plus secant is 2 secant x. Positive 1 and negative 1 canceled. So, guys, I think we are definitely heading in the right direction here. I've got the 2 that I need. I do not like the fact that this is a binomial. I'm wondering if we can use a Pythagorean identity to turn this into a monomial. Is it? Which identity are we looking at? So we've got tangent squared x plus 1 is equal to secant squared x. So that would mean that tangent squared x is equal to secant squared x minus 1. So we could turn this into a tangent square. Now, how am I going to turn that into that? I don't know. Any ideas? I'm wondering if maybe turning everything into sines and cosines might be worth doing at this point. I don't want a fraction, but maybe if we turn everything into sines and cosines, we could make that fraction go away. Oh, here's another idea. Yeah, I don't know if that's such a good idea. Let's try turn everything into sines and cosines. Let's see what happens. I'm going to leave that 2 out front times the fraction 1 over cosine x. And this would be sine squared x over cosine squared x. I'm trying to keep on the screen where we're headed with this. I think I'm just going to copy it over here so I can keep my eye on it. 2 cotangent x cosecant x is where we're trying to get to. This is just sitting in the back of my mind here. That's my squishy brain. Where to go from here? Any ideas? Should we turn this into, should we do the keep change flip thing maybe with this? Keep change flip. We've got something divided by a fraction instead of dividing by a fraction, multiply by its reciprocal. Let's try that. I think we might see something if we do that. I don't know. I'm hoping. There's a lot of hoping that goes on when you do these things. I guess a little bit of trust too. Trust that it's going to work out. Oh. Oh. What if we combine this? This is, well, then we're back where we started. Except it's all sines and cosines now. If I cancel this cosine with one of these up here, I got cosine x. This would still be a sine squared x. Ooh, I see it. Anybody else see it? No? All right, you finish it up. One of those fractions is going to have a cosine on the top, and one's going to have a 1 on the top, because that's the only way you're going to multiply and get cosine x. I want cotangent to come first, so we'll do cosine x and 1. Nice. Mic drop. All right. Guys, welcome to the wonderful world of trigonometric proofs. It is a really cool place. We dove into some really complicated, especially those last 2 proofs are going to be, I didn't do this to scare you. I just wanted to choose some proofs that we're going to give some opportunities to see some common strategies that you're going to use. What you're going to see on your assignment is going to be more similar to the first 2 proofs that we did. Okay, I'll show you. This is what I was working on before you guys came in today. It was doing some proofs for. Well, I'm making a solutions for the assignment. Now I'm not going to post these.